Welcome to the 2024 Vecellio Distinguished Lecture. I'm David Ford. I'm the Vecellio Professor of Construction Engineering and Management here in the VIA Department of Civil and Environmental Engineering here at Virginia Tech. A few logistics before we get started. This room has 2 exits on either side in the back. Should we need to evacuate, we need a meeting point, we'll meet at the mock-up of the facade mock-up that's out on this side should we need to. We have several people to thank for the opportunity. First and foremost, thank the Vecellio family, whose endowment makes this talk possible. I'm pleased to recognize Mr. Leo Vecellio, who's here with us. Thank you. There are people here at Virginia Tech that really support our program. Julie Ross is the Dean of College of Engineering. She can't be with us today. Mark Widowson is the department head of the Civil and Environmental Engineering Department. And Brian Kleiner, wherever you are, Brian, is the head, thank you, in the back is the director of the Myers-Lawson School of Construction. I also thank Penny K. Litton, who is our hostess, and our fellows and scholars. So one of the important things that the endowment, the Vecellio Endowment, does for us is it allows our program to financially support deserving students. And these are our fellows and scholars. And this year we have 4 fellows and 4 scholars, and these are them, but I'd like to take just a couple of moments to introduce them to you. Avi is here. Avi is from India. He has a lot of construction experience, 18 years of it in the Middle East doing high-rises in hospitals and metro regions. He is also the TA for my Introduction to Construction Management course. I can tell you it's the first time my TA has ever had more industry experience than I, and so that we're more teaching as a team than we are as an instructor. He plans on going into academia when he's done here at Virginia Tech. Jessica is one of our fellows. She's from here in Virginia. She's worked at the Rand Corporation and with Hensel Phelps and McDonough. She plans on first going into construction practice and eventually coming back into some form of academia to help teach construction management, either at the high school and or university level. Sarah is here with us somewhere, is from Fredericksburg, Virginia. She's been an intern at Whiting Turner and a TA here. She plans on continuing to work with Whiting Turner as a project engineer. She is just one example for those of you who are students about the importance of internships in developing that relationship, and clearly they lead to job opportunities. I suggest you follow that. TZ is from China and has worked as a TA here and worked in facilities management as an intern and plans on going into academia when he finishes. Max is one of our scholars. He's from Burke, Virginia. He's been an estimator with Archer Western and is a member of the Corps. He plans on getting an engineering management degree from the United States Air Force Institute of Technology and then joining as a civil engineering officer. Corin is from Freehold, New Jersey, has worked with Whiting Turner in higher ed and waterfront projects, and is particularly interested in improving our structures as they are faced with increased number of natural disasters and eventually getting her PE and LED credentials. Zach, somewhere, is also from New Jersey, has worked with Fletcher Creamer and Kimley Horn, and plans on working on designing hydraulic structures. And Lindsay is our representative from the West Coast. Lindsay, she has the most traveled award from our fellows and scholars. She's from Washington and has worked with GLY Construction and Port of London and plans on putting together water resources and construction, which ought to be a very valuable combination. Please join me in celebrating these fellows and scholars in our program. The Vecellio Endowment provides an opportunity for Virginia Tech and the wider construction industry to learn from a distinguished member of our industry. The Virginia Tech motto is ut prosim, that I may serve. So one of the questions that I think should be foremost in our minds is, how can we in our construction industry fulfill that motto and that obligation? How can we put that into practice in our engineering and construction practice? As engineers, we are people that are using science and technology to make the world a better place. And as construction engineers, we are planning, developing, designing, and building and operating major infrastructures to benefit society, corporations, and individuals. In the largest of those public infrastructures, we're improving the lives of thousands or more people, an enormous impact. But developing these mega infrastructure projects creates both opportunities and a special set of challenges. One of those challenges comes from the fact that these mega infrastructure projects are both very big and very complex. They're very big so that the advantages and benefits are magnified, but that also means that the challenges and the impacts that we need to address are larger than mere mortal normal-sized projects can absorb, so that they're particularly important. They also include a large number of very diverse and interacting parts. We have project partners and other stakeholders that are trading responsibilities and rewards and risks. We have construction teams that are coordinating these complex development dynamic dances of all of the resources that it takes to put these projects together and to complete them. And we have project managers for each of the major participants and others who are managing those resources to optimize the objectives not only of the project, but of their own organizations. So what that does is it makes the management of these large mega infrastructure projects both a very challenging and dynamic project control issue. Second, mega infrastructure projects are often, I would say usually, technologically advanced. Think back in history where we have developments in bridge truss designs and cabled-stayed bridges, just as two examples of how the technologies that have been coming out of these large projects have been moved the industry forward. Now we have other new technologies. We have automated construction like robots that are tying rebar. And as we know, lots of surveying that's being done by new and developing technologies. Developing and using those technologies in untested environments and projects is a particular challenge in figuring out which ones will benefit our projects and how. Third, and finally, mega infrastructure projects take a really long time. We measure the lifespans of these projects not in years, but in decades. And therefore, the teams evolve themselves. And the teams have to respond and adapt the projects to the changing conditions that they occur throughout their long lifespans. One of the common impacts of these characteristics is an increase and diverse set of risks. Risks to meeting the project cost, schedule, and performance goals. What are those risks for these mega infrastructure projects, and how can they be managed for project success? Today, we're going to learn from our speaker about one of those mega infrastructure projects and some of the challenges that that team has faced and how they've been managed. Ryan Banas earned his civil engineering degree from Case Western in 2008. He worked as an assistant construction manager for Parsons Brinkerhoff, after which he moved to HNTB, where his bridge projects have included the new Tappan Zee Bridge over the Hudson north of New York City and several projects here in Virginia. In May of last year, he was chosen to be the project director of VDOT, Virginia Department of Transportation's Hampton Roads Bridge Tunnel Expansion Project. He'll give you a lot more detail on that. Ladies and gentlemen, please join me in welcoming the 2024 Vecellio Distinguished Lecturer, Mr. Ryan Banas.
Good afternoon. Day after Halloween. How's everybody doing? Rested, sober, maybe? It's okay. Well, first and foremost, I want to thank you for giving me the opportunity to be here. Mr. Vecellio, this is an honor that I will carry with me for the rest of my career. I will tell you, many of my coworkers here in the Commonwealth are very jealous of the spot I stand today, and I take this honor very seriously. So thank you for your stewardship here at the university. Thank you for the wonderful students, giving them the opportunity we had a chance to meet with today, to learn about them. That is all through your generosity. Professor Ford, thank you as well. I thank you now. You may not thank me later, but I promise I'll do as best a job as I can this afternoon. So to start my lecture here, I look at this title and you may be saying, what is this guy saying? What they didn't teach me in engineering school? A little bit daunting when you walk into a room, and that's where we are, right? A lot of your lecturers probably in this room are pretty close by. But when I was in your shoes sitting in a similar place, I was terrified, right? I had to be ready to graduate in a couple months and figure out not only how I was going to pay the bills, what I was going to do with my life, but how was I supposed to step into industry with 4 years of experience in engineering, working out problems, and know exactly what to do every single day, competing with people 15, 20, 30, 40 years my experience, right? Terrifying. When we walk away from this presentation today, my hope is that I can share with you how I found a way to think about my education a little bit differently. A little bit of a different perspective. Perspective makes all the difference, folks. The other thing that I hope you take away from today's lecture is to appreciate how noble and important a profession you are about to enter when you leave these halls, when you leave this campus. There is no more rewarding, honorable profession than being a civil engineer, a civil servant. Professor Ford mentioned thousands of people. We're going to blow that number out of the water today, folks. We're going to touch the lives of billions of people. We'll walk through that. Now, before we get going, I think it's really important that we get to know each other a little bit more. Now, I apologize, I'm going to start with myself here, and I want to go back to the very beginning. November 12th, 1980, and I promise I won't do this. So, all right, we won't go back that far. Now, I'm born and raised in the great state of Michigan, a little town called Maybe, Michigan. That's not a misprint. We have 2 E's. Very southern portion of that town, of that state. Place I'm very, very proud to come from. Now, that picture there, that is the business that my parents bought from my dad's uncles. My dad is a first generation born U.S. citizen, son of Polish immigrants that came here to this country, and his uncle started that lumber and hardware store. My entire youth was in that store or on our farm in Maybe. That store represents to me the love that I came into, the place that I came into, my love for building and building things, whether it was houses, barns. I didn't appreciate it at the time, but the fundamentals of picking up cigarette butts in that parking lot, I'll tell you, they paid off. At least my dad tells me that. But I'll tell you, I held every job in that business that a young man could hold, dusting shelves, sweeping floors, and going to those construction sites, delivering materials to somebody's homes weeks after weeks, and seeing them eventually come to a place where people called home, that inspired me. Now, that inspiration drove me to Case Western Reserve University, again, they did a pretty good job educating me, okay? So let's give Case an easy time. Maybe not as well as Virginia Tech. They did pretty well. And at Case Western, that's where I entered the civil engineering program. And in that map, as the upper right shows, that's really just the start of my journey. A small farm town kid, leaving Michigan, going to Cleveland, Ohio. And from there, my career really took over. I took opportunities very similar to what you're sitting in now. As a student chapter president of our American Society of Civil Engineers chapter, I got an opportunity to go to Florida. When I was in Florida, I met somebody, and that somebody gave me an opportunity to go to Seattle and interview for a job. And that same somebody gave me an opportunity to move to Washington, D.C. and have my very first job ever. I got that opportunity literally drinking beer and eating chicken wings. So when you're hanging out after class on the weekends and your parents are telling you, what are you doing to your future? You can tell them you were just planning. You were trying to make it work. You're trying to make that connection. Now, as you move through your career, much like I have, your projects turn into your children. I'm very proud of each and every one of these. That upper left, that's the Route 1 interchange up in Northern Virginia, my very first job out of college. Project I was very proud to work on. If you know anybody that has ever worked on the Woodrow Wilson Bridge, pretty sure they've got a tattoo hidden somewhere. Then I had the opportunity to move to New York City, to Manhattan, my first taste of tunneling, where I worked on the New York City subway system. There I met my wife, who's with us tonight, and that's when I found out if you want to meet the pretty girls, you get into tunneling. Right? Spitting proof of it right there. But from there, I took an opportunity. I wasn't quite happy. I met my wife, but I wanted to find something else. I moved down here to Virginia. I moved to Virginia 13 years ago for 2 years. 13 years later, I haven't left because of the opportunity that exists here. I had the opportunity to work on the Gilmerton Bridge, the largest oscillated drilled shafts in the United States at the time. Pretty cool feature. From the Gilmerton Bridge, I went over to the Elizabeth River Tunnel project there, the upper left, where we built one new tunnel and rehabilitated 3 others. Then moved off to the Chesapeake Bay Bridge Tunnel. This is when I found out that I'm kind of getting sucked into this tunneling world, so be careful. They come and get you and they won't let you go. We had the opportunity to build another parallel tube there across the Chesapeake Bay. But last but not least, I ended up at the HRBT. Now we talk about opportunities, something I'm going to talk about later. This is nothing that a small farm town kid from Michigan thought he would ever do. I wasn't the top of my class at Case Western, guys. If it wasn't for partial credit, I wouldn't have had a degree, I'll tell you that. I think we were talking about some students' imaginary numbers. They're still imaginary to me. I'm not sure quite what they are. But that's enough about me. I want to get to know a little bit about you, maybe test your understanding of where I'm coming from today. So how many of you grew up in Virginia? Raise your hand. Okay, fair amount of folks. All right, you've all spent time in Virginia, obviously. So I want to frame this a little bit better with where I'm coming from when we talk about the Hampton Roads Bridge Tunnel Expansion Project. So here's a map. That is Virginia, right? We're all familiar with that. Hampton Roads. We are a collection of 17 municipalities, 17 cities. We can't get our act together. We don't know what to call ourselves. Hampton Roads, Tidewater, Virginia. We bounce back and forth. I call it Hampton Roads. Now, I also think it's important to maybe put in a little bit of context on where we are. So let's see if we can add some color. Okay, so Washington, D.C., all right. Everybody knows Washington, right? All the decisions are made there. Move down to Richmond, right? Familiar with Richmond, right? I think they've got some statues there, the big cigarette just south of the city. I think it's still a cigarette now. Our friends there in the smoking industry, tobacco industry, big important part. Areas of higher education. Oh, wait, there you go. That's right. Other school in Virginia. And then here at Virginia Tech. All right, so now we all know. So when we talk about the Hampton Roads Bridge Tunnel, can I ask how many of you have driven through the Hampton Roads Bridge Tunnel? Okay. How many of you have driven it through it more than once? How many of you have driven it through it at least once a month for a period of your life? Once a week? Once a day? Oh, man, you are unlucky, sir. I'm sorry. So Hampton Roads, we're a very, very unique region. Here are 3 main river crossings. We have the James River Bridge up there on the left, the Monitor Merrimack Bridge Tunnel there in the center, and then the Hampton Roads Bridge Tunnel down there on the right. Now, this regional landscape of Hampton Roads, this water, is what makes us so important to our economy, so important to our national security. First and foremost, we are home to the largest naval base in the world, in Naval Station Norfolk. Actually, in Hampton Roads, 80,000 active military service members live in this region each and every day. 15 branches of the military, or 15 installations in all 6 branches of the armed services. We're home to one of the largest container ports on the eastern seaboard. We handle 30% of all U.S. coal exports right there in Hampton Roads. On top of that, we are a 48-hour drive from 75% of the U.S. population. So why go to Baltimore? Why go to New York? Why go to Savannah? If you go to Hampton Roads, you can get anywhere in 2 days, with the exception of California. We don't need them anyway, right? We're just kidding. On top of that, we have 1.7 million residents. Actually, that's a wrong number. It's 1.8 million residents, let alone all the tourist traffic that comes through our region, either going to the Outer Banks, Virginia Beach oceanfront, or up the Eastern Shore. The things that make us great, this water, this regional landscape, are also some of our biggest challenges. As you can imagine, all of those people, all of that freight, all of that military presence, the importance that it puts on our region. So when we talk about the HRBT, I always like to say it's more than a tunnel project, and I'm going to be honest, we're going to talk a lot about the tunnel today, folks, but it is. In all, we are a 10-mile corridor. We start up in Hampton, there on the left. We work all the way down to Norfolk. Now, I live just south of this map. When we talk about resiliency and sea level rise and handling stormwater appropriately, I live just south of this map. The elevation outside my house is 5.8. So when we talk about sea level rise, we talk about high tides, king tides, talk about a stiff breeze out of the west, we have water problems. So the HRBT is aimed at doing one of many things. First, we're increasing capacity. We're easing congestion. We're also enhancing travel time reliability. This crossing right here was designed to handle 60,000 cars a day. Right now, it's pushing more than 100,000. In addition to that, that infrastructure was designed decades and decades ago. We weren't worried quite the same way. We weren't treating stormwater the same way. So now we're raising this facility throughout, helping with that stormwater, helping with that resiliency, sound walls, intelligent traffic systems, all the things that go along with one of the most heavily congested transportation networks on the East Coast. Now, this video we'll play next walks you through what the HRBT is and what it will look like. Now, as we leave here, this is Hampton. 4 lanes of gridlock. For my friends who've driven this every day, you've seen this before. But there on the bottom, you can see our new 8-lane configuration. Now, as we near the shoreline, something I really want to point out here, something that, again, they don't teach in engineering school, right? I didn't learn this. Look where these bridges touch down, so close to the existing bridges. That overlay is actually in space where this will occur. Our 15-acre island expansion here coming to fruition. And then now you are diving into one of our 2 new tunnels that we are constructing across the harbor. Now, we're going to jump up on the south side. You'll never go quite that fast. It's 1.5 miles, but we'll have you moving. And now you see our 8-lane mega trestle, our 8-lane bridge handling all of that traffic across the rest of our harbor. Now, this project, we've known that the HRBT was a major bottleneck in Hampton Roads for decades. Actually, in 1990, our General Assembly here asked VDOT to study that crossing. It took us decades to come to a solution. The reason for that is right-of-way impacts. So many people in this area, the Navy, Hampton University, and HBCU, a VA hospital, historic cemetery. This project, in its current concept, has 3 right-of-way impacts on $3.9 billion of construction. We're borrowing 15,000 square feet from a university we'll give back. We have a dock owner who happened to build on VDOT right-of-way. The city permitted it. We asked them to scoot back just a little bit. And then we've purchased a property that was fallen in disrepair. But to think about that, $3.9 billion. That was a political motivation we needed to find. How do we minimize that to overcome and actually deliver this project? 30 years in the making, 30 years after we identified that need. Now, a little bit about our project. At $3.9 billion, we are VDOT's largest ever single construction project. Now, a lot of folks here may have been familiar with Northern Virginia, I-81, work we've done all over the state. As I like to remind my friends, we are triple, quadruple many of those projects at $3.9 billion. Another part I'm very proud of is how we funded this, right? This is something they didn't teach me about in engineering school. How do you fund a project? Well, for us in Hampton Roads, $3.9 billion is not something that you come up with quickly. So what we did in Hampton Roads is we passed through the General Assembly a small sales tax that goes directly back into coffers in Hampton Roads so our local elected officials take that money and invest it in projects of regional significance. Project of regional significance in Hampton Roads is greater than $100 million. Now that revenue stream, that 0.7%, is about $200 million a year. And if you do that quick math, 200 million to 3.2 billion, right? If it's 92% of 3.9. Well, you do that by taking that service. Hey, I'm good for 200 million in revenue a year, and you take it to the bonding market and they sell bonds, just like you would take your pay stub to the bank and get a mortgage. Without that foresight in our General Assembly and our legislature, we would not be building this project. So that's about where we are, how we are, a little bit about me, got to know a little bit about you. Let's talk about tunneling, right? Because tunnels are cool, right? You with me? So here in Virginia, little did I know, we are the largest collection of immersed tube tunnels anywhere in the world. Now I would have thought, if you asked me, I would have thought Holland, right? They got a lot of water dams, they know how to build. Asia, South America, different parts of the world. No, right here in Virginia. In fact, in 1957, VDOT was the first agency in the world to build an immersed tube tunnel between two artificial islands in 1957. Now, an immersed tube tunnel, if you're not familiar, an immersed tube tunnel is a long stick of concrete pipe. Now, when I say long, 300, 350 feet in length, 40 feet wide, 30 feet tall. We build those in a dry dock, we float them down the river, we dredge out the river bottom where we may want them placed, we bring them in, we immerse them, backfill with stone over the top, and you have a tunnel. Pretty simple, big Legos. We've done that, like we said on this map, 10 times. We are world experts at that. But with that method of construction, there are a lot of challenges. Now here, that bottom left photo, that is the Midtown Tunnel, about 2013, 2014. If you look in the upper right corner of that photo, a very infamous bridge in the background that I'm sure you've all talked about in your classes. That photo on the right, that is Corpus Christi, Texas, where the original HRBT was fabricated. With this type of tunneling, something we're very good at, there are some challenges. Now think back to our regional landscape. First and foremost, we have to find space for this. Now we have ship repair. We've got Navy ships, we've got cargo ships. Trying to find that dry dock space, extremely expensive, extremely hard to find. We also have to worry about maritime considerations. We have 6,000 regulated ship movements across our channel each and every day, let alone the Navy, who really doesn't like to tell us when they're bringing an aircraft carrier through or a submarine. It happens quite frequently. You also have to worry about the tides and the weather. We're in Hampton Roads, you're on the ocean, right? You got to worry about that coming through. In the case of Midtown Tunnel, it took us about 4 weeks to fine grade, bring in a segment, immerse it, and backfill over the top. One of our segments, 3 weeks into that process, getting ready to immerse the tunnel, we had a storm come up in the afternoon, minor storm, right? Rain, wind, and tides, completely destroyed 3 weeks worth of work. Start back at square one. So when it came to the HRBT, our engineers were tasked with, how do you consider all of those variables of our region, all of these variables here, and come up with the solution? How do you take all of those into account and find a way to move a project we've been trying to execute for 30 years forward? And their solution, our solution, involves 3 very, very important pieces of equipment. German hype music, guys. Come on, it doesn't get better than this on a Friday afternoon, right? Meet Mary, the tunnel boring machine. Turn it down a little bit here. Fully electrically powered, Mary uses 10 megawatts of power, or the equivalent consumption of about 6,000 homes. At 430 feet in length, she is the largest tunnel boring machine of her kind ever fabricated and the second largest in North America. Here at her factory in Southwest Germany, it took us about 15 months to fabricate this machine, upon which we went through a factory acceptance testing and fully dismantled this machine, shipping it over here to Virginia. Now, as you look at Mary here, she is actually not in her full 430-foot configuration. So when we talk about tunnel boring machines, we think about them as cutter heads, shields, and the rest of that is trailing gear. My analogy for that is a train. You have an engine, right, that drives the train. That's our cutter head and shield. And then behind that, you have train cars, or we call trailing gear or gantries. Those provide support functions. In ours, it may be ring building, utilities, hydraulic power. Each of them have their own unique purpose. Now, when you try to take into scale what this may look like, now a lot of folks say, all right, those are European cars, they're not that big. Well, that's a Jeep, right? That's a Jeep. You guys have a lot of those out here at Tech. I've seen them in the parking lot, right? Pretty darn massive machine. Now, when we say that Mary is the largest tunnel boring machine of her kind ever fabricated, you've got to explain that a little bit. It's kind of like cars, right? We have electric cars, we have gas cars, we have diesel cars. Well, Mary is a tunnel boring machine. There are hard rock, there are slurry, there are earth pressure balance. She is the largest variable density slurry tunnel boring machine ever fabricated. Second largest in the US, only behind Bertha, is a tunnel boring machine in all. And if you've heard about Bertha, I see some smirks. Hopefully, we do a little bit better than Bertha did. Now, one of the things I love about our cutter head, we talked about our region, is what we have adorning it. That flag is our regional flag of Hampton Roads. The green, the pastures, the blue, the sky, the white, the water that unites us, and a star for each of the 17 municipalities that we represent. I thought, very, very befitting of our machine. Now, what makes us unique, we talked second largest, only the third bored vehicular tunnel in the US when we complete. You have the Port of Miami, Seattle, we slide in at number 3. No impacts to the navigable waterway. We're not dredging. We don't have big equipment out there in the middle of the river. We are drilling beneath the bay bottom. Our segments come in by barge. Our spoils go out. We're not adding to the already congested roads. And last but not least, I say the postman's creed. Nor wind, nor rain, nor sleet, nor snow, right? 24 hours a day, 7 days a week, we can get at it, we can mine. That weather doesn't bother us at all. Now, a lot of folks want to know why the name Mary. Very famous person we named that after. But the reason for that is, if you can imagine, you're a miner, right? You're working on a tunnel boring machine. You're down 173 feet beneath the surface, completely black, 90 pounds of pressure pushing in on you. You become religious pretty quickly, right? Well, the patron saint of miners is St. Barbara. And in St. Barbara's honor, we name our tunnel boring machines after women of significance. Now, we opened a naming competition. The school children in Virginia Beach selected Mary Jackson. If you've ever watched the movie Hidden Figures, Mary Jackson is the first black female engineer at NASA. Very humbling for us to think of how recently in our history she was going through those challenges. And we thought, since Mary was a pioneer and we were pioneering in Virginia, how befitting that we have her name honor our machine. All right, so we've got a tunnel boring machine, right? That's piece number 1. But it takes more than that. You also have to have a way for that tunnel boring machine to operate. So we have slurry. We're a slurry TBM. So slurry, right? Water, bentonite, clay. It's a mixture. No different than what you use in a drilled shaft. Exactly the same type of material, except we use it horizontally rather than vertically as you do in a drilled shaft. Now, when we go down and we push that slurry down to our cutter head and we mix it with those soils and bring it back to the surface, we have to find a way to pull the soil out of that slurry. It's very important for us. We want to reuse that slurry to the best of our ability. Our slurry treatment plant, as you see behind me, is capable of handling 16,000 gallons of slurry a minute, or a fully loaded dump truck every 10 seconds. This equipment can pull material out of slurry half the thickness of a human hair. It is the largest slurry treatment plant in North America, costs $30 million, as compared to Mary, our tunnel boring machine's $70 million price tag. We like to say in construction, we don't want a dime holding up a dollar. We're not going to have cheap infrastructure holding up that tunnel boring machine. And these two pieces of equipment work very incidentally together. The TBM does not move without the slurry treatment plant, and vice versa. So just like our tunnel boring machine, we took it upon ourselves to name our slurry treatment plant after Katherine Johnson. And again, if you've seen that movie Hidden Figures, Katherine Johnson was a female that John Glenn said, I want to make sure she checked my calculations. She was that human computer. And we thought, since Mary and Katherine worked so well together in history, that maybe we could get a little bit of their luck here at the HRBT. So now we've got a TBM, we've got a slurry treatment plant, but we have to build a tunnel, right? We've got to leave something behind us. And I mentioned in immersed tube tunnels, 300 to 350 feet in length. And for us at the HRBT, that dimension goes down to 6.5 feet. Every 6.5 feet, we put in one of our segmental concrete rings. This is what's known as a universal ring. Now, shown here in the upper left photo, that is a multi-service vehicle we use to transport material and equipment in and out of the tunnel. That is carrying 3 stacks of 3. That's because for our rings, we have 9 segments that make up each and every ring, the last being this white segment, which is a key, no different than an arch. The last one that goes in provides that rigidity. Each of those segments, 18 inches thick, 16 feet wide, 6.5 feet wide, weighs about 20,000 pounds. As that bottom right photo shows, we use black steel reinforcing around the perimeter. Now, in that photo, that segment is flipped upside down, right? We're gonna be in the precasting process. We also fill that with steel fiber reinforced concrete, and we love steel fiber because steel fiber is very resilient in multiple dimensions. So if you think of a bobby pin you may have laying at home and you cut it in half, you now have 2 of our steel fibers, just about. We mix that into the concrete, and the beauty of steel fiber is that when it rusts and it corrodes, it does not create enough tension in the concrete to cause spalling. It's very, very resilient. We really, really like that steel fiber. At the end of the day, we will need nearly 2,400 of our 6.5-foot rings to build both of our new tunnels at the HRBT. TBM, STP, and now we have segments. So how does it all come together? If I had to take that analogy and put it into simple terms when I'm thinking about what's most practical, if you think about an old school vacuum you may have at home, right? You've got the long wand and you've got that head agitating down on the carpet. Well, that's our cutter head, no different, right? It's agitating. And then you've got the canister over here, but between the two, you've got a long hose. Well, we have 2 hoses. That's our slurry pipe, right? We've got one going down. We pump clean slurry in. We got another one coming up. We're bringing that dirty slurry back to the surface. And now it goes to our vacuum canister, right? Our slurry treatment plant. Pull out liquid from the solid. We send those solids away for disposal. You're mining. It's easy. Big Legos. I don't remember them teaching me that in engineering school. But it's big Legos. Now this photo here, this is the best one to describe everything that we do at the HRBT. So one thing that's really important to comprehend is that our cutter head is 46 feet in diameter, second largest in North American history. Very proud of that fact. But our liner behind it, as you see here, is 44.5 feet in diameter. What that means is our tunnel boring machine is bigger, and as we're mining, we're actually extruding that liner. Now, as this photo shows here, we've got 2 partially erected rings, and that would never happen in practicality. It's just a small cutaway that we use right here. Now, how this works in mining is those hydraulic rams fully extend all the way out. We call that stroked out when they've pushed as far as they can go. At that time, we take one of our rings that's being delivered beneath the tunnel, and segment by segment, we slowly retract a few pairs of those rams. We move our segment in place, we then pin it against the previous ring. We do that around the entire circumference. You have all of your hydraulic rams now retracted, and then you start driving yourself forward, 6.5 feet at a time. 1,191 times, and you've got the first bored tunnel in Virginia history. Now, how do we keep our folks from becoming inundated? And this is really novel technology, right? Professor and I were talking, we always want to go to a complex solution, and usually it's the easiest one that wins. Easy for us, we have our shield, we have our liner, and right here, we have rows of brushes. And between those brushes, they're wire brushes, we inject absolutely enormous amounts of grease, and that grease creates a watertight seal. Our staff that are on the tunnel boring machine are in atmospheric condition. If they ever had to go out and service, enter out into the chamber, the pressure chamber, they would experience pressures up to 90 PSI. That is deep diving. We have to get OSHA variances to put crews in that. We have hyperbaric chambers where we slowly bring people down under pressure, allow them to enter and work, bring them back out, and then slowly bring them back up. If you've ever read the book, The Great Bridge, or heard of the disease called the bends, decompression sickness, that's what you get if you go out in that pressure chamber a little bit too quickly. Very, very important that we do that carefully. The coolest piece of everything here, and they definitely didn't teach me in engineering school, was how you steer a 10 million pound machine 173 feet down completely in the dark. And the secret is in our ring. So I mentioned that this is a universal ring, and that means that every single ring that we put in this tunnel is exactly the same. All 1,191 of them, they're interchangeable, identical. The secret comes into the measurements that make up those rings. So I told you they were 6.5 feet wide, and that's half true, I can say, half true. The bottom of that ring is 6.5 feet wide, is represented by this model here. Now this model, imagine this is a full ring, and in our practicality, it would be hollow in the center. But the top, you can see, is a little bit thicker. And in our case at the HRBT, 6'6" at the bottom, 6'8" at the top. So as we're mining, using GPS technology to know exactly where we are at any given point in time, and we stacked or arranged subsequent rings, all big sides together, all small sides together, you can get a curve. Or if you rotate rings and their orientations, front to back, big to small, small to big, you get a straight tunnel. So we move a 10 million pound machine, 6.5 feet, 6.5 feet at a time by using a 2-inch deflection. Now, we're designed to stay within a 4-inch tolerance. Pretty lofty when you're thinking that weight. We were able to do it in our first tunnel, not veering more than 2.5 inches on its trajectory. An absolutely amazing feat. So what do we have? What are we going to get here? This is our existing tubes, our eastbound tube going towards Norfolk, our other tube coming back from Hampton. The 2 tubes on the right, those are our 2 new bored tubes. Now, something I didn't appreciate in engineering school was that tunnels want to float really, really badly. That is one of the biggest challenges in tunneling is they want to come up. So our immersed tube tunnels here on the left, you'll notice they're much shallower, but when we dredge them, we backfilled over them with rock, and rock by nature is typically heavier than the soil that we have. In our case, we dug deeper, and we like going deeper for a few reasons. First and foremost, we get that additional overburden. We get that additional force so that we don't float, something that's very important. We also get down into a good geological formation. Now, Hampton Roads, rock is hundreds, if not thousands of feet beneath us. We are in the Chesapeake Bay. There is no stone. If you find stone, you go talk to my friends at another tunnel project down the road, and they'll talk to you about claims and construction delays. They've had a lot of challenges with that at CBBT. Very important for us to be down, and we're offset because at the end of the day, our existing tube needs to continue to be in surface, right? We're 2 lanes in each direction right now. At the end of the day, we will be 4 lanes. So part of our scope, part of our project, we will be converting that existing tube, be flipping traffic around, worrying about ventilation, lighting. As you go into a tunnel, did you know that the lights are brighter? Did you know as you come out, they may be dimmer or brighter depending on the time of day? We always look at your eyes. What are your eyes doing? We don't want your eyes to dilate or contract too fast. I didn't teach me that in engineering school. Very cool part of our project. And again, 173 feet below the surface where we are mining, drilling horizontally. Now our cross section shown by this model here and also up there on the wall, we have jet fan ventilation there in the crown. We have 15 feet, we're 12 to 15 feet. We build this nice, big, beautiful tunnel from the invert to the crown, 41.5 feet. We fill in nearly 15 feet of that with nothing but stone and asphalt to get to that riding surface. That egress corridor there on the right, in the event of an evacuation, you would get out of your vehicle, walk over there and slide open a big door. When you open that door, fresh air smacks you in the face. We do that because we don't want smoke to follow you into that corridor, right? You want to go into that safe haven and have a way to walk to safety, so we pressurize it so that that smoke stays in the roadway. 15,000 truckloads of material to fill in the bottom of that tunnel. I think even more crazy is 1 million square feet of tile to go on the walls. I renovated my house, and I did like 15 square feet of tile. It took me like 4 or 5 months. You can ask my wife. She reminds me about it all the time. 1 million square feet of tile. But we love that tile because it helps with cleaning the tunnel. Right? We want to keep the walls clean, any vehicle emissions. But it also helps with reflectivity, right? We want to cut down on lights. We can use LEDs, but if we can have fewer lights, more reflectivity in the tunnel, that's good for us. It's cheaper for the taxpayers. All very, very important parts. So we talk about progress at the HRBT. I always like to keep it in historical context. And I think pretty much every piece of construction that we've completed has some pretty darn significant historical context. Here in this first photo, you can see on the right, that is the first bridge crossing the HRBT in more than 50 years. Now, if you notice from our video before, right, we're building those bridges in the same footprint of the existing, so we've only widened or built that bridge to 2 lanes at its landing and 4 lanes further on. We'll eventually demolish that bridge. Now, we're also very concerned about sustainability, right? That's a newer word. We weren't talking about it when I was in engineering school. So how do you find a way to be sustainable when you're demolishing concrete? Well, we found a partnership with the Virginia Marine Resource Commission, and we're taking all of those bridges that we're demolishing and putting them as artificial reef in the Chesapeake Bay, creating new fish habitat. The piece of history I like to think about when I look at this bridge, when I got the opportunity to stand out there at 2 a.m. on May the 3rd, and the first traffic went across it, was the 800 million vehicles that drove on the bridge to which we were taking out of service, that existing bridge, 800 million vehicles. Now remember, 50 years in service approximately, and it was designed to handle 60,000. Our new bridges are designed to carry more than 100,000 a day and have a service life of more than 100 years. Professor, thousands, I'll raise you billions. Billions of people on that bridge that civil engineers will impact. How much cooler does it get than that, guys? Now here, more cool, more mile or record-setting construction, building a 15-acre island. Now that's something, again, I never thought. I saw videos when I was in engineering school about Dubai. I didn't think I would get to do it. But here you can see we built a 15-acre island expansion. Really interesting story. When we built that berm and we went to start backfilling, we found a sea turtle in there. And you can't just bury a sea turtle. They frown upon that. So after weeks of skiffs, nets, fishing lures, and bait, the turtle would not go away. Now, I don't know all of the acronym, all the meanings, but his name was Teddy, but his nickname was WTF on the project because we could not get rid of this damn turtle. So as the story would have it, and I was not there, this was prior to my tenure, we opened up the berm and went away. And after a long weekend, we came back, and the turtle was seen swimming somewhere a little bit away from the project, waving a fin, and they started closing the berm and built the island. So I go with that story. I don't want to really know the details. But here you can see we've built that island expansion. We filled it in, and right here, that is our tunnel boring machine poking out here at that new open approach. Depths of 65 feet, we have had to dig this receiving pit to receive our tunnel boring machine. That's the ocean right there. Imagine the immense water pressure. I did dam analysis, but not 65 feet of head pressure when I was in college. I don't know about you guys. We've also set other records. Weekend before Thanksgiving last year, our contractor pulled off the largest continuous concrete pour in Virginia's history. A fully loaded concrete truck every 3 minutes for 31 hours. 5,480 cubic yards. Now, unfortunately, we have a time-lapse video, and it's about as exciting as it is watching concrete dry, all right? But it was a 153-foot cell. I mean, those are some of our crew members down there standing, to give you perspective for size, and 8 feet thick, all in 31 hours. Absolutely impressive. Taught me a lot of things when I was in engineering school, delivery rates, how to account for curing, wet loads on forms. How in the heck do you try to figure out when you can get 31 hours straight of concrete service and nobody run out of gas? Nobody have a flat tire, no plant breakdown. I'm going to tell you the secret to this one. You don't, you just get lucky. That is the answer. And sometimes, better lucky than good. As we jump over to our South Island, we have our slurry treatment plant, right? That's Catherine separating all that material. We have a wastewater treatment plant, but really we want to focus on our tri-cell. This is where Mary was launched from. This area was excavated down to depths of 80 feet. Again, immediately adjacent to the ocean. We use that area now for feeding all of our tunnel operations. I will say a masterclass in logistics when you think of all the men, equipment, materials, spoils that have to go through this tunnel. Our South Marine trestle, right, that 8-lane mega trestle, look at that bridge. That is absolutely massive. Now, the girders on this, I'm a pretty big guy. Those are 85-inch girders. Some of the biggest pieces of precast I've ever had the opportunity to work with. Our piles, 4.5-foot piles, massive, going across that harbor. You can see the intricate construction. And I talked scheduling. I was taught just-in-time delivery. I wasn't taught how in the heck do you maintain 4 lanes of traffic, building a $3.9 billion project with turtles, and you can't drive too many extra piles, and you have folks that live in Virginia that literally have license plates that say, I hate HRBT. And that's what we have to contend with, folks. Our contractor did it. They found temporary bridges that they built here where we shifted traffic out of the way so we can build our new bridge to handle that traffic, and all coming down into there. There are so much that goes into this project that I never learned in engineering school. We get down onto our land side, right? We've got bridges we're widening, new decks we're reconstructing. We demolished bridge decks with 18,000 PSI water pressure. You can demolish concrete with that, and then we come back and we pour new bridge decks. Cool, it's 18,000 PSI. We've got the Navy, right? They definitely didn't teach me stakeholder management in engineering school, right? We've got the Navy right there. We actually, part of I-64 in Virginia, VDOT doesn't own the right-of-way. The Navy does. And the Navy didn't like what we were doing. They told us to stop multiple times. I'm like, no, guys, sorry, go home, right? So we found a way to make your neighbors nice as you put your picture on your wall, right? So you put a frigate up there on our sound walls. So I'm not gonna say you wanna put your neighbor's picture everywhere, but it's not a bad idea. The star of our show, right? The tunneling work. This is the part that I get really excited about. This is Mary, right? She's getting ready to launch. This is April of last year now. Again, her 4th trailing gear, her 4th rail car, she's too darn big to put together all in one shot. It's sitting right there. These are the segments that we feed the Mary slurry treatment plant up there to the left. Here is a view inside the tunnel. Now that left photo, that is a multi-service vehicle, again, delivering segments up underneath that tunnel boring machine. That photo on the right, that's what the tunnel looks like about 2 weeks ago. You can already see we've built that roadway. Notice on that right wall, those slurry pipes going through the tunnel, right? Very important for us. We've got a power cord there, compressed air, fresh water, all kinds of things working through there. Our best day, 17 rings. Our best week, 50. I'll actually argue with that. I think the very, very best day at the HRBT can be summed up in this video. We talk about days in our life, days in our career. I'm gonna say this, getting married, because she's sitting right here. Getting married, it's always there, honey, I promise. Birth of my children, maybe one of them, the other one we're not so sure about. That day, April 17th, 2024, when that TBM, after 1,191 rings, 7,941 feet, broke through that head wall, you had 400 people going nuts. I hugged grown men. I hope I never hug again. I hugged them that day. That was a day I will remember forever. Now that is, in tunneling world, if you've never been around a tunnel boring machine project, that photo on the left, when your lead superintendent comes through that cutter head and he puts his hands up in the air, shivers, man, I'm telling you. That day was absolutely amazing. As a civil servant, civil engineer, knowing that day we were one step closer to impacting billions of people. That's not the only cool thing, though, we've done, guys, right? We got to move it, right? We've done one tunnel, right? We've bored a tunnel, you can imagine, right? We broke out. We got to bore a second tunnel, so you have to turn the machine around. Now, that machine, I mentioned before, 9.8 million pounds, very, very, very heavy. Now, the cutter head and shield right there, that is 2,500 tons in and of itself. Putting it in different terms, about 2 billion paper clips, right? Pretty heavy. Now, if we were to pull this apart, that's months of pulling it apart. Then you rotate it, then you put it back together. There are no conventional cranes that are gonna pick up 2,500 tons that we have anywhere here in continental US. Just not gonna happen. So how in the heck do you do that? I went through the FE manual, I went through the PE practice programs. They never taught me this, right? Well, we use some really, really simple novel technology. This is a cradle. This white structure is a cradle that holds a TBM in place. These right here, these orange devices are hydraulic jacks. They help us level the tunnel boring machine. We want it to be nice and level sitting there. On the bottom of the shaft, we have steel plates, a little bit of grease, but the secret is what happens between the bottom of this jack and that steel plate. And in that gap, we inject liquid nitrogen because at atmospheric conditions, what does the liquid nitrogen do? Boil, yeah, boils, right? And when it boils, it turns to air. When it turns to air, it expands and you have a nice little cushion. And we were able to reduce the force of friction on this machine by a factor of 100. 2,500 tons down to 25 tons. Now do your static friction calculations, right? Your kinetic friction calculations on that. It's a big difference. We're able to move this machine using chain falls and winches. It was the heaviest and biggest diameter ever done in the world. Our friends over in Europe did it. They wrote a magazine about it. They got stories. We're gonna publish this one soon. I'd like to give it back to our friends. Good friends across the pond, but I like winning. This video shows exactly what that looked like. Now, again, not as bad as watching concrete dry. This is one single 11-hour shift that we rotated 2,500 tons versus months of disassembly and reassembly. Absolutely earth-shattering, absolutely record-setting. Very cool. They didn't teach me that when I was in engineering school. So where is Mary today? Very proud. Mary, here you can see, she has turned around. I didn't look in my phone, I have an app. As of a couple days ago, Mary was in 8 rings, 93 feet. Here you can see, there she is mining, and that's the back of her cutter head as she's starting to mine her reverse trip. This is where she broke out. Gantry 4 still out there in the waiting. You can see her trailing gear come behind. I'll tell you at the end of this, we're gonna put up some links. You may have seen them around campus on how to follow us on social media. We're probably not college age cool. All right, guys, we try, we're old, we try, but we have some pretty cool content on what Mary does. Please follow us. We're hoping 51 weeks to complete that first tunnel, 11 million man hours to complete that first tunnel. We think we can do it a little bit faster here on our return trip. Before we get I want to talk about a few more interesting challenges, and I guarantee when we go through this, I'm not even going to say it, I'm going to say it once. They didn't teach me this, okay? They definitely did not teach me this stuff. Now, when you step onto a project, you know there are going to be environmental challenges. That's part and parcel what we do. It's construction, right? We're out in the environment. But our island, our South Island, where we launched Mary from, was the home to the largest colony of nesting birds on the eastern seaboard. Now, many of those nesting birds are protected species. And if a protected species comes in and creates a nest in your construction zone, you have to give it a 50-foot buffer. You have to back up 50 feet. Now, on our project, that means shutting down cranes. A $3.9 billion project shut down by a bird making a nest. Now, with consultation with the Department of Wildlife and Recreation, they allow us to take a certain number of nests. Now, taking a nest, we humanely harvest them. That does not mean making an omelet. As I've learned, we do not make omelets out of the eggs. We humanely harvest them, or we have to let them become, right? They have to become chicks and then fly away. Or option 3 is you get our 4-legged friends here, run around and scare the bejesus out of them and hope they go somewhere else. So what we did every single year to this day, between April and September, we bring in 3 barges that we cover in sand, and we encourage the birds to go nest on. Did not teach me, I don't remember dog courses, dog breed selection courses in engineering class. I was 2 months into this project, driving home, dodging traffic, and somebody called me and said, Ryan, we found a bone on the project. So I've dealt with bones, and it's 3 feet long. The heck do you do with that? Well, for us, photo on the right there, during our excavation, we found the keel of a ship, stone, and the bone, the femur of a cow. And working with William and Mary, we discovered that that was from a shipwreck in 1823. Now, very similar to a lot of the other history we have in Virginia, we were building Fort Monroe, the largest stone fortification in the United States in 1823. That's where we found that shipwreck. On the left, cannonballs. During our excavation, we have found 9 Civil War era cannonballs, 4 of which we have had to detonate. On one of my previous projects, it's not just HRBT, Gilmerton Bridge, demolishing a counterweight. Get a call at 6 a.m., Ryan, we found shells on the project. I said, shells? Shells. Okay, I'm thinking shotgun shells. It's parts of Chesapeake, it's not always that great. Okay, we have our rough areas too. I go out and I look down at the counterweight, and there are 6-inch diameter, 18-inch long military-grade shells that were cast into our counterweight. And 20 feet off our project limits was a fertilizer plant. That is about the worst combination I can think of. So at 6 a.m., I get on the phone and call the state police. We get Navy unexploded. I called my wife and said, hey, did you see they shut down the road? I made that call, right? That's some of the fun stuff you get to do as an engineer, right? They didn't teach you that, but you get to do it. And we uncovered that. So 9 Civil War era cannonballs here. It's not just HRBT. This stuff is everywhere in our field. But by and far away, the coolest thing we've ever found, the thing that nobody in their mind could have ever taught me, was what we found almost exactly 1 year ago. During excavation of our tunnel, our first tunnel, one of our slurry treatment plant operators, now, as that slurry is coming off and we've got a conveyor belt taking those spoils, it's going pretty quick, but you can see things from time to time, but it's moving pretty darn fast. He said, stop, I found something. We stopped all operations, he punched the button, conveyor belt stops, TBM stops. Somebody said, who didn't pay the power bill? We said, no, that's okay, we did. And we ran out there and we picked up what we didn't know what were at the time. They looked like rocks, but they happened to be, oh, come on now, the remains of a mastodon. Were mastodons in the Commonwealth of Virginia. Actually, we are the furthest east a mastodon has ever been recovered. Mastodon very closely related to a woolly mammoth and an elephant. They are older, they go back 27 million years. Woolly mammoths and elephants go back 7. Woolly mammoths and elephants like green leafy vegetation. Mastodons were like goats. They ate woody brush, and you know that by their teeth. Mastodon actually means nipple tooth, so that is the tooth of a mastodon. 12 to 50,000 years old. We got that. They said, Ryan, what do we do? And I'll tell you the other thing they don't teach you in engineering school is get the smartest people you can to surround you. So I looked at my smart people and said, please tell me what to do. We worked with the Virginia Natural History Museum and we had the artifacts restored and we were back mining. How cool is that? Mastodons. And the best part is when I went to pick those up from the museum, they literally gave them to me in a piece of Tupperware. Like what? Right? All of the things that we experience in our career. You know, this slide talks a little bit about all of the things that we've done at the HRBT, right? We're one project in one corner of the Commonwealth. I talked about 5 other projects, I think, to start. I don't know, there's probably 80, 90, 100 of you in this room. Think of the projects you're going to work on. Think of the projects that you're going to have lists like this. Think of the billions of people this room will impact. Wow. Pretty cool, guys. Pretty darn cool. You are entering that profession. How cool is that? What I still haven't told you what they didn't teach me, right? How do we handle all of this? Engineering school did not teach me about the most challenging technical concepts I would ever encounter. True, fact. Won't deny it. I guarantee it's the same for you. You guys go to Virginia Tech. Better than that other school in Virginia, I'll give you that, okay? They're not gonna teach you everything you need to know. They can't. You guys have I've got to meet your faculty. They are some amazing folks. They can't teach you everything you need to know. Can't, they're trying. Engineering school taught me one thing. This is perspective, folks. All I'm gonna mention here is perspective. Engineering school taught me one thing. Engineering school taught me how to solve problems. That's all it is. There is not a single problem that you have calculated, performed, or looked at to date that you will solve as an engineer in the real world. What you have learned, what you are learning, what you will take with you into industry are the fundamentals of how to solve a problem. You're going to look at that problem and go down and break it down to its root, to its smallest, most minuscule pieces, compartmentalize them, and use the fundamentals you have been taught here to learn how to be an engineer. Professor Ford, you mentioned the definition of an engineer. If you look on AI, I looked on it the other day. It says engineers use mathematical formulas and equations to solve problems. I think there's some other adjectives in there, right? Think about that. Think about I put it in perspective. We've talked about today on campus other professions. What do doctors do? They remember stuff, they heal us, okay, whatever. Architects, I don't even know. I like architects, they're okay. Guys, we're here as civil servants to solve problems for people who don't know they need us, but without us, holy smokes, are they in trouble. You wouldn't have gotten here today, you wouldn't have flushed the toilet, you wouldn't have brushed your teeth, you wouldn't have done a darn thing had it not been for a civil engineer. You, every one of you in this room, is going to be one of those. So I'm going to say this now. Welcome to the club. Welcome to the club of changing lives from this day forward. Every class you take from this moment forward, change your perspective. You are preparing yourself to change lives. Billions of lives this room will change. I got a shiver in my spine right now. I'm not joking, guys. That's how impactful what we have the opportunity to do is. How fortunate are we? So, in closing, I got a couple things I want to leave you with today. 3 things I want to leave you with. So my first ask is to close your eyes. Trust me on this one, it'll be for just a brief moment. Close your eyes. How many people were wearing blue shirts in the room when you closed your eye? Open your eyes up. How many people were wearing blue shirts? Anybody know? I don't. How many opportunities pass you by if you're not looking for them? If I told you that we were going to be looking for blue shirts, that you would have counted every one in every row, right? 8 rows, 20 people a row, you would have known. How many times in your life are you just moving, going through the motions, walking to class, going through your next assignment, going to your next job, worrying about what's for dinner, and you aren't looking for an opportunity? Opportunities are not given, guys, they're taken. I wouldn't be in the position I'm in today if I didn't take an opportunity. I took the opportunity to go to Florida. I took the opportunity to go to Seattle. Took the opportunity to go to New York. Took the opportunity to be in Hampton Roads. I don't really think I took the opportunity at HRBT. I think it was kind of forced on me, but it's a different story. Blame the commissioner. Some of you met him. But you have to take opportunities. They are not going to find you. You have to find them. You have to look for them. So look for your blue shirt. When there is an opportunity to go meet with the professor, meet with Mr. Vecellio, go to an industry event, take that opportunity, go. Sitting back, not going to happen, guys. I am looking to hire every able-bodied person I can. Everybody in my profession is doing the same. We don't know where you are if you don't come and find us. We don't know what you're interested in if you don't come and tell us. Find your opportunity. That first and foremost. Second, this is one my boss at my current job told me about 2 weeks into my job, and it has changed my life, and I will carry this with me forever. I can get it to come up. Don't ever negotiate with yourself. You walk into a room, you want 10 things. If you say, I want 10, I'm going to ask for 6. Guess what? You might get 3. You walk in and ask for 10, you may get 7. Don't negotiate, guys. When you walk in and you want something, you need something, if it's a promotion, if it's a project, right? I've heard this quote. When I walk into a job interview, what should I ask? What should I say? I think it's a wonderful question. Wonderful question. How can I be assured that I will be put on the most impactful projects for this company? Whew. Man, you're not negotiating with yourself then. Most impactful? I want to have a job. I want the most impactful projects. Man, that means something. Somebody says that to me, whew, look out. Be working for them someday, right? Don't negotiate with yourself. If you want something, ask for it. Worst they can say is no. Never got hurt from a no. And last but not least, this one was of much debate. Me and my wife, I had a coworker helping me with this one. The more interested you are in other people, the more interesting you are to other people. When you meet somebody and you ask about them, when you care about somebody, their career, how they're doing, what they're doing, they will naturally be attracted to you. They will naturally want to see you succeed. There is nothing better than two people interested in each other's success. When I met that gentleman eating beer, drinking chicken wings, he was interested in me. He wanted to know, Ryan, why are you here? Why are you over here by yourself? Man, okay, hey, how you doing? We started talking, right? My wife did that to me as well. She was interested in me. I couldn't help it. Be interested in other people. You will succeed when the people around you succeed. I mentioned it before, finding smart, interesting people to put around you and work alongside. There's nothing more rewarding, and you will rise higher together when you do that. Be interested in somebody. If you haven't read it, I will swear it's the best book you can read. Dale Carnegie's How to Win Friends and Influence People. If you guys have not read that, I kid you not, I got out of college, I was living in Northern Virginia, couldn't meet a girl to save my life. I read that book, and I know I've met my wife. I love you, Jacqueline. It's true. It teaches you how to be interested in other people, how to want to learn about others. And if you can do that, you will fly so high. The hardest part about everything I talked about here, and this they won't teach you in engineering school. We talked about it earlier today with some of the faculty. They will not teach you this in engineering school. Hardest part that we deal with, people, right? People. The dirt doesn't care how you wrote the email or talked to it, right? The concrete doesn't dry any quicker because you're screaming at it. They got open traffic in an hour, right? Do that to people, it will, right? We'll have some problems. Hardest thing is people. But if you learn how to work with people, and those are skills that only you can develop, that you can go out and meet with people, talk to more people, read a book, see what they're interested in. It's really easy for me here. Hey, you guys like Virginia Tech? I mean, all of you are wearing it, right? Be interested in people, guys. That will carry you so far in your career. So with that, said it once, I'll say it again. Welcome to the club, guys. Billions of people. Sounds good. Thank you. Q&A? Okay. All right, so they said we're allowed to do a little bit of Q&A. They're not kicking us out yet, so I will take any and all questions you guys have. So fire away. Yes, sir.
So you said that one of the best days you have is 50 rings. So is that a 24-hour shift or like 12-hour shifts? And what's the rate of advance?
Yep, so our rate of advance depends on the geology that we are in. We have seen it right now. We're pushing 2, 3, 4 millimeters. Rotation will get up to 10. That 17 rings in a single day, those are 3 8-hour shifts. We do run 24/5 when we are mining. Saturday and Sundays, we reserve that for maintenance. As you can imagine, Mary is a 10 million pound machine. She requires a lot of maintenance. We use a lot of grease for that watertight seal. We use a lot of grease on Mary's parts. She is a massive, massive piece of equipment that needs a little bit of tender love and care a couple days a weekend to make sure she's doing okay for us. Other questions? Yes, sir.
What do you do with Mary when you're done with the tunnels?
Oh, sweet Mary. When we are all done, Mary is a $70 million behemoth, our sweet girl. Mary will be cut up and sold for scrap. These tunnel boring machines, they're very unique. Her cutter head there that you're looking at here, this is a great view after we started doing some maintenance on her cutting implements, her rippers and scrapers, her rollers. Very custom designed for our geology. Now, I didn't mention this before, but if you've read in the news in Virginia, there is another Chesapeake Bay Bridge tunnel, another tunnel boring machine operating right now, 10 miles down the road from us. The TBM that hit an anchor, you guys may have heard that, right? 10 miles away, Chessie, their machine, totally different machine than ours. So these are so custom made. Also, I mentioned that this machine was fabricated in Germany. Trying to ship back all of this weight to Germany just doesn't make economic sense. So pressure vessels, big hydraulic rams, electric motors, those will be sold back to the manufacturer, but the large majority of Mary will be cut up and sold for scrap. I think I had another hand starting to come up over here. Yes, sir.
How much was the depth of soil, overburden soil?
Yeah, so at our deepest point, we've got about a 50-foot channel. Mary's about 40 feet. So we've got about 80 feet of soil above us at our deepest point for that overburden. That does vary throughout our trajectory. So at the islands, when we first start our descent, we are much shallower. So in those areas, we have to still be concerned with buoyancy. So as you look in photographs, you follow us online, as you come in those first few rings, 40, 50 rings, we will put temporary concrete blocks in the bottom of the tunnel segments so that the interior liner doesn't float. Now, a thing for us in Hampton Roads, big concern are hurricanes, high water events, nor'easters. So we do have special calculations performed and plans in place that if we see a high water event coming to, we bring in additional ballast, we bring in additional equipment and park it in the tunnel or on top of the tunnel to add that additional ballast so Mary does not want to float, or the tunnel does not want to float. Yes, sir.
I have a couple of questions that are related. So when you go, have you compared it to cast in place or the injected in place concrete versus precast concrete, and how do you seal the joints if you do precast elements?
So for the precast liner, so the joints, so around the perimeter of every single segment, there is a rubber gasket that goes around the exterior. That rubber gasket is on every single segment. So as we butt segments together, those come into contact. Now, we mentioned that Mary is using those hydraulic rams and pushing off of that previous liner. Each of those rams, I think there's 37 in total, are each pushing at a minimum of 100 kips. It is that pressure that is causing those gaskets to collapse and collapse and expanding and providing that watertight seal. Now, as a secondary measure, on the interior of each of our segments, and I know it's really hard to see in this model, but there are two dimples here in the very middle, and those are alignment cones. Those are cones for shear cones. Those shear cones help us. So once the segments are delivered to the tunnel boring machine, from that point forward, they are picked up and placed with vacuum suction. We don't use mechanical grabs, we use vacuum suction to move them. They help align that vacuum suction. But their secondary purpose, inside one of those alignment holes on each of the segments is a plastic insert that's threaded. We can thread into that insert, punch a hole in the back, and inject grout behind the segments to provide a watertight seal if those primary rubber gaskets do fail. Yes? I'm sorry?
How does safety and safety regulations go on in such a large project?
How do safety and safety regulations go on such a large project? So our contractor partner is running a staff of just safety employees of about 20. We have our own safety oversight as VDOT as the owner. We did mention some special OSHA variances that we have had to have for our deep underwater diving. I would say our project, Professor Ford was talking about mega projects. We really break our project into much smaller areas as we look at it. So we run it at a macro, but we manage it at the micro. So overall, our safety statistics at HRBT, something we're very proud of, trend well below national averages. I will tell you to date, we have had one fatality on the project, an absolute unfortunate freak accident where we had a car go in the median on the interstate, jump between two overpass bridges, and a surveyor was down on the surface street below. Happened, I think, back in 2019, very unfortunate circumstance. But we will say one fatality, one recordable injury is one too many. So it is something that we are constantly monitoring, constantly discussing. Safety is first and foremost the most important thing. I'll share, you asked, I'm gonna share it. When you guys are driving through our work zones, each and every one of you do it, I have to remind myself, you're driving through somebody's office. I'm very proud that when I first got out of college, I spent my first several years in the field, the majority of the time. And I'll tell you, on my very first job, 2 weeks in, I had a car almost hit me in a lane closure. I was measuring striping in Northern Virginia. I heard the tires lock up. And I went back to our HR benefits the next day and got extended disability. And that's not a joke, that's serious. It is real, it happens all the time. So as you are driving through our work zones, put down your phone, focus on the road and drive safe. I cannot tell you how imperative that is for me. I have small children at home. Every single one of HRBT, 2,000 people working on our site every day, every one of them has somebody they go home to. It takes a second for somebody to make a mistake behind the wheel. I've almost made them myself. I will ask as we talk about safety, be cognizant of that. You are taking somebody else's life into your hands every time you enter our work zone. Other questions? Yes?
How many people does it take to operate a machine of this size?
So to operate the machine itself, on the machine, 17 individuals running Mary at any given time. Per shift to support the mining operation is 60. Because you have the TBM, you have segments being fed, you have segments being fed at the land side, you have crews bringing in barges, and you have spoils disposal. 60 people, 3 shifts a day, 5 days a week. A lot of folks, very specialized jobs, the majority of them. Our project, we joke that it's the United Nations of projects. We have folks from the East, Germany, Italy, France, Spain, Russia, Algeria, South America. We have folks from all over the world because the equipment that we're working on is so very specialized. Other questions? Fire away.
So for these machines, I know that at this depth the clay is relatively tough, so it can wear down on the bits. How does the process go for replacing the bits while you're mid-dig through the tunnel?
Yep, so for us, the wonder we have here in Mary is that many of her cutting implements, and you can see those here, some of them are darker because we've already replaced them, they are interchangeable pieces. So I mentioned hyperbaric intervention. So for us, if you think of our tunnel boring machine, her cutter head, I'm gonna grab my model here. So shield cutter head, right? Our cutter head has depth to it, it's thick, right? This isn't a mistake. So the way I always think about it is in that thickness, we have, I can't give it a better analogy other than a shell, right? I don't say a bullet or a casing, it's a shell. So in a shell for a gun, right? You've got the casing and you've got the projectile, the bullet. That's exactly how the majority of our cutting implements are. They live in that housing, which is the shell. We can go through the back of the cutter head, unbolt those housings, pull them back, and they come out and they're about waist high. We can then swap out the round, right, the expendable bullet, the tip, swap them out, put that back in, and then slide that casing to the back of the cutter head. Now, if we have to do that underway, that requires us to do a hyperbaric intervention where we bring in those divers who are dry, but they're diving under high pressures. So the lifespan of our tools, typically we change out those tools 2 to 3 times throughout the journey. Now these round disc cutters that you see right here, we only use those in hard rock or concrete environments. Now, Hampton Roads, we don't have rock. But when we break out of our launch pit and our receiving pit, we do have concrete for our supportive excavation. So at those times, we break through. Once we get through, we are so shallow, and we are in the very first portion of our ground is improved soil. We are able to do those interventions without going hyperbaric, so we can do them without pressure. Other questions? Anybody over here? Yes, sir.
So I have 2 questions. So one, what was the estimated economic output that's going to come from having this new tunnel being built? And then second, you talked about having 2,000 laborers on site. What was the labor constraints that you dealt with during the procurement part or going into that?
Yeah, so the estimated economic impact of the second tunnel and the HRBT expansion project is $4.6 billion to the Hampton Roads region. As it relates to resource constraints, that was a very large part of the project. So our workforce, so we say it's staff and craft, right? So we have staff inside, engineers, superintendents, project managers, all the way through accounting, logistics folks, they're running at about 2,000. That was a risk our contractor took on when they entered this market, when they decided to bid the HRBT expansion. Our project did have a hard cap at $3.3 billion. Our contractor came in at $3.299 billion. Now, I will tell you, I wasn't there during procurement. If somebody comes in at that number, they probably found a way to try to trim some things at the very end. And labor, as we've seen in the market, as we've seen across the country, not just in Hampton Roads, continues to be a challenge and probably a place they pulled back that number. How are we doing on time, sir? Few more?
One more question?
One more?
If any?
Yes, sir.
So you said you used nitrogen to move the big head. How'd you move the rest of the body?
Yeah, so the rest of the gantries, great question. So the rest of our gantries were between 350 and 425 tons. For those picks, for those individual gantries, we used 2 800-ton cranes. Those cranes were on the surface of the island. We reached down in, we picked those gantries up, we slid them over, rotated the cranes, and placed them on an SPMT, which is a self-propelled modular transporter, as I've come to learn. If you've ever seen what NASA uses to move a rocket into place, right? That's a type of SPMT. We had our SPMT. So our SPMT then took those gantries, moved them forward, and did a 3-point turn, rotated it 180 degrees. Those 2 800-ton cranes then picked them up, put them down in place, and set them back down into our excavation. Big, big, big cranes, I will say.
Let's thank Mr. Banas for his talk. We have a couple of things for you to help you remember the event, but for all of us, you're welcome to join us at the reception. Go up to the third floor, 300AB. Is that correct? Okay, and you can there's elevator here, steps here, and Mr. Banas and the fellows and scholars will stay for a moment, and then we'll join you. I hope we'll see you there. Thank you very much.